Alright, my name is Muhammad HARIZ and I will be presenting about the Fourier series analysis. So firstly, we go to the time domain, and given the value that our lecturer gave us is 200 kilohertz, we input it as f0. T0 equal to 1 over f0, and tau is given in the instruction as 0.5, the width of the pulse in seconds. T as the time vector scaled by t0, and then we skip this one. The xt and xn is for the zeros, and next we go to the plot side, which is the first one. We need to have 3 harmonics, which is 5 harmonics, 10 harmonics, and 20 harmonics for the time domain. So this is the part of coding for the plotting of each harmonics. And then this under here, after the line 44 is the equation for xt, which is xt equal to xt plus x times exponent 1j times 2 times pi times n times f0 times t. So if we run this code, we will get the time domain for every harmonics. Let's try to run this. So this is the signal in time domain for the first part of Fourier series analysis. The first one is for harmonics 5. The second one here is for harmonics 10, and the last one is for harmonics 20. Okay, then we can go to the next part, which is the frequency domain of the Fourier series analysis. So as the previously input value, which is 200 kilohertz, and for this part, for frequency domain, we have to perform fast Fourier transform coding for MATLAB, which is given here from line 12 until line 15 for the length of the signal, sampling frequency, and frequency vector. And the middle part here, line 17 until line 46, is the part where we plot the frequency domain of the previously time domain signal. So you can see some part of the coding for frequency domain that is similar to the time domain to generate the waveform, to generate the signal in frequency domain. So if you run this code as well, you will supposedly get like this three signal for each harmonics lah. We get 5 harmonics for the first one, the second one is 10 harmonics, and the third one is 20 harmonics. So the difference for 3 harmonics right here is hardly can be seen. You can see a little bit of difference, which is on the right side. So right here we have like a really flat right side, and this one it grows a bit, it leans a bit on the right side, and this one is pretty much symmetrical for the 20 harmonics.
Hello, my name is Brian Jordan Wilfred, and my matrix number is CE210035, and today I will be demo on how we get the frequency response for the frequency cutoff of 1200 kilohertz. So the first thing that we did is we get the transfer function, and then we calculate the gain in decibels, and then we also put the variable for the frequency cutoff, which is the FC, into 1200 kilohertz, because for our group number 5, we are assigned to use the frequency cutoff of 1200 kilohertz. And then we plot the frequency response using the function of semilog x to plot it, and then let's try to run, and we get this frequency response for the signal of frequency cutoff 1200 kilohertz. So that is all from me. Thank you.
Okay, and I'll be presenting the time domain part. Okay, and this is our coding for time domain. So we have done it, and then we have to actually stimulate it in the MATLAB, and then we will actually run the program like how I'm doing it. So yes, we put in the value of the fundamental frequency and all that, and then yes, this is the one. This is the value of 0.5 and the low pass filter parameters. When we list down all the parameters, the cutoff frequency over here, and yes, and we also put in the filtered signal with the harmonics. Okay, and once we inserted all the values, okay, then we insert like 10 harmonics and everything, and we have to plot it real color, and it continues till the end. Okay, so yeah, so it's in the 20 harmonics. Okay, once we actually filled in, now we have to run it, and then we can get the signal graphs. Okay, so here we go, and then we have all the graphs over here, the filtered signal for 5th harmonics, 10th harmonics, 20th harmonics. Okay, so this is actually the converted time domain signal, okay, which is the time which is in frequency domain, is filtered by actually setting the values of certain frequency components in the array of the alpha, which is filtered. Okay, so we actually set the frequency to 1200 kilohertz. Okay, so that's when we actually getting the values. So here are all the graphs. Okay, so from the result we actually can observe that the signal in time domain will be actually become more distorted while the harmonics actually increases. You can see on the graph over here. So therefore, from the results we actually can conclude that the time domain graph shows how a signal changes over a time. Then it will become original signal when the harmonics actually increases. So it is because of the number of overshoots at the discontinuities, which is proportional to the height of the discontinuity as well, according to the Gibbs formula. Okay, so the signal is reconstructed by adding Fourier series, then overshots as appeared around the edges. So we can see as the 5th harmonics and all that. So this is what happening over here. So according to the findings, we actually found out that the harmonic is actually growing while the signal time domain actually increases. So the harmonic increases while the signal time also increases. So because in this the signal is actually converted from a time domain to a frequency domain. So that is when the amplitude of the signal decreases.
Assalamualaikum, my name is HARIZ ILMAM dari ZULKURNAIN. My matrix number is DE200114. So for the low pass filter, I'm gonna tell you about the frequency domain. So this is the coding of MATLAB of our project. As you can see, the fundamental frequency, fundamental period, second, width of the pass, all the value that you input into, and then we do the coding for the 5, 10, and 20 harmonics. So this is the formula, and then just follow, and then we run it. This is before the filters. Okay. So, and then we run it as a sorry for lagging. Okay, the data finally came out. So this is the frequency domain signal for 5 harmonics. As you can see, it has the harmonics, and this is the for the 10 harmonics and 20 harmonics. All the value has harmonics. So what we want to do is to filter it. Okay, so this is the the coding for the filtration of the harmonics. So we do the same process, same value, and then just add on the X. There another formula for this. So this is the formula for the filtration. Then we do the okay, you see, okay. This is the coding, and then we just run. So this is for the filter. Okay, we run. It takes a while. Okay, so the data will come up. Here, as you can see, okay, we able to put the frequency domain. The frequency domain for the 5, 10, and 20 family able to be filtered. That's it.
Hello, my name is EMERSON and my metric number is CE210029. And my part is I will investigate the effects of having a lower or higher duty cycle, then set the duty cycle for the case of tau 10%, 20%, 30%, 70%, and 80%. Okay, we go to the MATLAB. Okay, first of all, this coding is used to generate and plot a periodic signal using exponent form of Fourier series. It demonstrates the concept of representing a signal as a sum of complex exponential functions with different frequencies and complex coefficients. Okay, in this coding we just need to change the tau. So for this coding, the tau is for 50%. So in this one, we need to find the 10, 20, 30, 70, and 80. We simply change it to 0.1 because 0.1 is when you 10%. When you change it to decimal, it becomes 0.1. Okay, we simply run it. Okay, this is the figure that you got for the 10%. Okay, for 20%, you simply just change it to 0.2. Then simply run. Okay, this one is for 20%. As you can see, there are significant changes in the +1, +2, for the n, +1, +2, and then this is the sum signal. Okay, for the third one, we change it to 0.3 for 30%, then simply run it. Okay, this one is for 30% of tau for the duty cycle. And then for the fourth one, we change it to 78. We go back to this one, and then back, and go to the 73%. Okay, this one is for 70%. As you can see, there are a lot of changes in the sum of signal or coefficient +1, +2, and +3. There are a lot of changes. Okay, for 8%, then you run it. Okay, this is for the 70% and 80% of the duty cycle. As you can see, there's changes in here, this one, because the the changes is happen if you change the value of the tau. Okay, for the overall, by adjusting the tau in the given code, we alter the width of the pulses in the generated predict signal. This change will influence the duration of the high amplitude region, the speed of variation in signal, and the frequency content, with different emphasis on low and high frequency components depending on the specific value of tau. For example, in our assignment is 0.5. Okay, that's all for my part. Thank you.
Okay, so this is a circuit for the time domain. What I did is I get the block of signal from workspace, and then inside this block I get the signal of xt from the workspace, which is this equation over here. This is the signal, and then I pass it to the absolute block, and then from this block I pass it to the time scope. This is for the original signal, and then this is for the filtered RC low pass filter signal. Inside the subsystem here, we got the equation for the low pass filter, and the equation is V in minus V out equal to RC times with the derivative of V out. And then we chose the resistor value to be 10k ohm, and then the capacitor value is 35 millifarad. Okay, so let's run the circuit, and what we get is over here. As we can see, the left signal is the unfiltered one, and then the right side is the filtered one. Okay, so that is all from me. Thank you very much. Okay, so right now I will demo on how we get the circuit for the frequency domain. Okay, so I got this block, which is a block called from workspace, and then I connect it to the FFT block, which is fast Fourier transform, and then I make it to be absolute. And then here we got the spectrum analyzer, which will show the frequency domain. The first spectrum analyzer is for the original signal, and then the second one is for the filtered signal. Inside this subsystem is the RC low pass filter, which is using the discrete derivative of equation, where the equation is V in minus V out, and then equal to RC differentiate V out over dt. And then the resistor value we chose is 10k, and then the capacitor value is 1.33 10 power of minus 3. And then when we multiply it together, the RC, we get the gain value of 0.133. And then for the XT time series, what I did to get this value is I export it, and then set the time t, and then the data, and input it into the real real function, and then with this xt time series value, I put it into the function of time series to get the time series of the data. So go back to the circuit. We will run this circuit. So what we get over here, there are two signals that we will get, because I put it two signal, two spectrum analyzer, and as we can see over here, this signal over to the left is the unfiltered one, and then over here to the right is the filtered one. We can see that there are some noise to the unfiltered one. And then when we pass it to the low pass filter of RC, we can get the smooth line of the frequency domain. So that is all from me. Thank you very much.